Let's look at the section Lagrange Multipliers. It's going to be the final, thank goodness, huh? The final homework set in your Survey of Calculus class. You're going to have a multiple variable function given. In this one, we're just going to keep it f of xy equals x times y. You're going to be given a constraint where the x and y values must adhere to some sort of an equation. For this one, now another thing, let me point out, your constraint won't be given with a gxy, but I always write a gxy because it's a second function of multiple variables. The technique for maximizing or minimizing a function over a constraint, there's a lot of steps. I try to do it the same way over and over, so that's the technique I hope to apply for you guys listening and following along. Okay, so the g of x, I put that there to represent a second function. It represents a constraint. All right, so what we're going to do is we're going to start this off by taking function f, derivative with respect to x, and setting that equal to lambda, which is the Lagrange multiplier, times the constraint having its derivative taken with respect to x as well. All right, so function f, if you take its derivative with respect to x, the derivative of x is 1 times y gives us y. That's equal to lambda times the constraint. Its derivative with respect to x is 1, 0, and 0. There's only one x term. Since it's straight up x, its derivative is 1. Solving for lambda, lambda is equal to y. I know that's hard to look at because lambda looks like an upside down y as well. After the x direction is done, then we go back, take derivatives with respect to y. Derivative of f with respect to y equals lambda times the constraint derivative with respect to y. For f, the derivative of y is 1 times x is x. In the constraint, its derivative with respect to y is 0, 2, and 0. So that's going to be lambda times 2. If you divide both sides by 2, then lambda is equal to x over 2. Once you've successfully taken both partial derivatives of function and constraint, isolated lambda in both situations, your next move, which if you're looking for steps, it would be like step 3. You set those lambdas equal to one another. Y equals x over 2. Step 4 is go to your constraint and substitute. You can either substitute the x for 2y or substitute y with an x over 2. Since we've already gone to the trouble of setting y equal to x over 2, we're going to go to the constraint and replace that y with x over 2. And that way, your constraint will only be in one variable instead of 2. So we're going to have x plus 2y, but we're going to use x over 2 instead of y, and that's equal to 4. Simplifying, x plus the 2's cancel, 2x equals 4, so that tells us x is equal to 2. We're going to remember that, and we'll put it in a box. back up here on step 3, I'm going to do this in blue. Y is equal to 2 over 2, because we just found x to be 2, which is 1. I'm going to put that in a box. And then finally, since we now have the point 2, 1, we're going to calculate f of that point. Go right to the very top left of the page. F of xy is equal to x times y, so that puts us at 2 times 1 equals 2. So our value is 2 at the point 2, 1. Let's look at another example of using Lagrange multipliers to optimize a several variable function over a particular constraint. Our function in this problem, we have x squared plus y squared. It's a 2 variable function. Our constraint given is 2x plus 4y equals 5. I'm going to change this to a colon. There we go. Okay, now using the same technique from the first example, we will start by taking partial derivatives with respect to x. Okay, so function f, if we take the derivative of it with respect to x, we're going to get 2x plus 0, because the y squared doesn't have an x. That gives us 2x equals lambda times the derivative of the constraint with respect to x. So that's going to be a 2, 0, and 0. So just a 2. Divide both sides by 2, and that gives us lambda equal to x. All right, let's remember that. Now, the next time through, we're going to do partials with respect to y. Function f, derivative with respect to y, is going to be 0. That term will be 2y. The derivative of the constraint with respect to y is going to be 0, 4, and 0, so just 4. Divide both sides by 4, and you will get lambda to be y over 2. Y over 2. Third step is to set the lambdas equal. X equals y over 2. Go to the constraint. The constraint is 2x plus 4y equals 5. Now, since we have x isolated and it's y over 2, we're going to replace the x in the constraint with y over 2. So that gives us 2 times y over 2 plus 4y equals 5. Our 2's cancel, so that's going to give us y plus 4y equals 5. 5y equals 5. That tells us that y equals 1. Okay, let me put a box around that. Change to blue like we did in the first example. If y is equal to 1, then x is equal to a half. So that tells us at the point 1/2, 1, that our function at that point is going to be half squared plus 1 squared which is a fourth plus 1 equals 5/4. And so we have optimized our two variable function at the point 1/2 and 1. We have minimized the function at a value of 5/4. The production function for a manufacturer is given by the function f of xy equals 100 times x to the 0.25 power times y to the 0.75 power. This is very similar to the Cobb-Douglas function, and it is. X represents the number of units of labor at $60 per unit, and Y is the number of units of capital at $36 per unit. The total cost for labor and capital cannot exceed $100,000. Well, that's our constraint. So let's take a moment to build our constraint. Okay, so labor is X at $60 each, so 60X plus capital, that's Y, at $36 each. And that can't exceed $100,000. So we've just built our constraint. Now, as far as the rest of the problem goes, we're going to tackle it like we did the first two examples. We're going to use partial derivatives, find lambda for each partial derivative, set the lambdas equal, go to our constraint, make a substitution, and then see what value of x and y we can come up with. And there are several parts to this problem that are I'm going to work it just like you see it in your homework. So hopefully I can do a decent example of explaining it and make it kind of easy to follow. Nothing about Lagrange multipliers is easy, but I'm going to do my best to explain this type of word problem, and that way you can get through the parts of your homework successfully. Okay, so first thing we're going to do is we're going to take our partial derivatives, just like we have done. We're going to do the derivatives with respect to x and y of the function given and the constraint we just built. All right, so the main function at the top, when you take the derivative with respect to x, we're going to have 100 times 0.25 and take 1 off the power. The y part of it stays the same. So let's do that. 100 times 0.25, that's 25, x to the negative 0.75. When you take 0.25 and subtract 1, you get negative 0.75. The y term remains the same because we're only doing a partial with respect to x. Now this is equal to lambda times, now the constraint, its derivative with respect to x is just going to be 60, just 60. The middle term and the constant, they have no x, so their derivatives default to 0, but we do have a 60 that's going to go into parentheses. We're going to come back to that. Let's do the partials with respect to y. In the original function, we have y, that part is to the 0.75. 100 times 0.75, and that'll take care of the y derivative. So that's going to be 75. Remember, the x part stays the same because this time we're taking a derivative with respect to y. 0.75 minus 1 is negative 0.25. The constraint's derivative with respect to y is 36. So that's lambda times 36. Now this next part, this is where we set the lambdas equal. And for this one, there's going to be quite a bit of algebra involved. Okay, the f sub x line right here, if we divide both sides by 60, that's going to give us 5/12. 25 divided by 60 reduced is 5/12. The x term has a negative exponent, so I'm going to write that x to the positive 0.75 down here, and that'll make the power positive instead of negative. The y is already exponent at 0.75. That's positive. I'm going to leave it on top. Equals. Now let's go to the derivative with respect to y, that line, that group. 75 divided by 36. I'm going to double check with my calculator. We want to write that as a reduced because we're isolating lambda in both of those lines. 75 divided by 36 as a reduced fraction, 25 over 12. 25 over 12. Okay. The x is to a positive 0.25. I'm going to leave it on top. The y is to a negative 0.25. I'm going to move it to the bottom, and that way the power will become positive. Because if you ever need to switch the sign of an exponent, you just move it across the fraction bar. Cross multiply. Cross multiply. You can do that when you have two fractions set equal to one another. That way you don't have to worry about a common denominator. Okay, upper left times bottom right. That's going to be 5 times 12, which is 60. Y to the 0.75 times y to the 0.25. What's 0.75 plus 0.25? That's equal to 1. We'll catch a nice break. 25 times 12, I'm doing the other diagonal, cross multiply. That's 300. X to the 0.75 times x to the 0.25. Add those exponents, and you'll get an x. A real clean x. They're both, y and x end up adding up to a power of 1. 300 divided by 60 is 5. So that tells us y is equal to 5x. In the constraint, substituting y with a 5x, that's going to give us 60x plus 36y, but we're going to write it with a 5x. is equal to 100,000. That was our total for cost, total cost for labor and capital. Now I'm going to have to go to another slide, but basically what we're going to do here is solve this equation for x, and then we're going to sub it right back into here to get y. And so on the next slide, I've got to do that. Continuing from the previous slide, we have 60x. I'm going to just recopy that last part. Plus 36 times 5x. It was 36y in the constraint, but we found y to be 5x. So we're going to make that replacement equals 100,000. That is going to give us 60x plus 180x equals 100,000. Okay, now from here we get 240x, combining like terms, equals 100,000. Dividing by 240 and reducing, it won't divide evenly, but in a reduced format, 100,000 divided by 240 will simplify to 1250 over 3. Now since y was equal to 5x, y is going to be equal to 5 times that 1250 over 3, and that's going to be 6250 over 3. Okay, so that gives us the point 1250 over 3 and 6250 over 3. Okay, I know it's a lot to keep up with, y'all. Going all the way back to the previous slide, our function was f of xy equals 100x to the 0.25 y to the 0.75. Subbing our values in, 100 times 1250 over 3 to the 0.25 times y to the 0.75 is going to give us, to the nearest whole number, and you're asked to round to the nearest integer in your homework, 139,321 units. That is part A. Part B, you're asked to find what's called marginal productivity of money. Marginal productivity of money, in other words, lambda. From the slide before, using either one of your partial derivatives results, you can write lambda equals, one of them we had was 5/12 x to the 0.75 over y to the 0.75. Now we can write that as y over x all to the 0.75, and we're going to make our substitutions. We've got a 5, 5/12. Let me trim that fraction bar up a little bit. There we go. Okay, so that is 6250 over 3 over, and the x was 1250 over 3, all raised to the 0.75 power. Excuse me. I'm going to rewrite that as 5/12. If you were to divide those two gnarly fractions in the parentheses, because they're really nasty, the 3's would actually cancel, because that's a complex fraction. If you take top fraction times the bottom one flipped over, the 3's will cancel, and 6250 divided by 1250 actually comes out to a really nice 5. Rounding to 4 decimal places, and this is what your homework's going to want you to do, is round it to 4 decimal places. You get 1.3922. That's part B. You were asked to find marginal productivity of money, but that's lambda. Part C. We're going to use that lambda to find the maximum number of units that can be produced if total cost is increased to 145,000. Originally, we were limited to 100,000, but we're going to up this to 145,000 available. Okay, so what we're going to do is we're going to take Part A's answer, 139,321 units, plus lambda, which we got to be 1.3922. Lambda is marginal. It's going to be that little bit of a gap increase. Now, originally we had 100,000. If we up that to 145,000, then we're looking at increasing the productivity on 45,000 only. Okay, let's look at that. That front figure is the number of units for 100,000. We have a Lagrange multiplier for that additional 45,000 that we're going to be allowed to spend. That's a $45,000 increase. So originally at 100,000 plus the marginal productivity for that extra 45 grand. Multiply that together and add, and we will get 202,015 units. We get to spend more, so we're going to make more units. What if that is moved up to 390,000? That's part D for me. Your homework, it'll be very similar. $390,000. Okay, so we're going to take our original value, the number of units we found for just a total cost of 100,000. That's still that 139,321 number. Having trouble writing. Let me try that again. $139,321 plus our marginal multiplier, which was the lambda. Now, compared to 100,000, this is 290,000 more dollars that we're allowed to spend. Okay, be careful in this final calculation. I'm going to double check mine. 139,321 plus 1.3922 times an additional 290,000. Let's see. $543. I still need to double check or triple check. 1.3932. Oops. Goodness. I need to make a correction real quick. I apologize, y'all. My Lagrange multiplier is 3932. So if you're wondering why I messed those calculations up, it was just human error. 3932. It's an easy fix though, but I know it's a hassle right here. Let me double check that calculation. Yes, so that number is fine, 202,015 units. It will make a difference down here, though, because I goofed that. That's supposed to be a 3. 2. Okay. I'm going to triple. That's why you always triple check, because it is very tedious. 3932. Okay. 543,349 units. I apologize for missing that calculation, but you see why I always go back and try to find errors, because they certainly occur. I know this problem is very long and tedious, and hopefully I wrote out enough steps to where you could follow along on your examples and your homework set. And good luck to you. The good news is this is the last video for the Survey of Cal class.